online.
Good afternoon, everybody. We have today another seminar of the Department of Atmospheric Science here at the University of São Paulo. And we have as a speaker Marqi Rocque, and she's a PhD student at the Colorado State University. Formerly, she also did a master's student there, and her bachelor in atmospheric sciences in University of Albany. She studies the very famous and beautiful thunderstorms in La Plata Basin in Argentina. So, Marqi, welcome, and the floor is yours.
Great, thank you. Thanks for having me. Share my screen here. All right, so as Rachel mentioned, I am going to be focusing on the influence of the Andes and the Sierras de Córdoba on MCS development in central Argentina. I'd like to thank my advisor here, Kristen Rasmussen, as well as Rachel, who's going to be hosting me in a couple of days, as well as all these people listed here and my funding sources. So I'll start with where are the most intense thunderstorms on Earth. This is a figure from Ed Zipser's paper in 2006, showing global satellite data. And what we see here is that there's a hotspot of intense convection in subtropical South America here in the form of high lightning flash rates. And when we extend this climatology to include the entire 16 years of TRIM, Bob Howes and colleagues at the University of Washington showed that indeed we do have this hotspot of intense convection in this region that occurs in the summer months, and you can also see it a little bit in the winter months. And these storms are known to produce significant severe weather in the region in the form of flooding, tornadoes, giant hail, and really large lightning. So it's really important to be able to understand these storms better. And prior to 2018, most of our observations of these storms were restricted to polar orbiting satellites such as TRIM. So you can see we have a TRIM precipitation climatology over South America here. We have hail identified from AMSR-E here, and as well as lightning across the region from LIS and OTD. And based on this satellite data, there was a conceptual model of the ingredients necessary for MCS development in this region, developed by Rasmussen and Howes in 2016. And there's three main components of this model. First is that we have a strong upper level trough coming across the Andes, and this generates a lee cyclone downstream of the Andes near the Sierras de Córdoba or SDC mountains here. And then we also have moist tropical air flowing in from the Amazon into subtropical South America here, along the South American low-level jet. And this moist air converges with southerly flow across the southern Andes, basically right along the SDC. So you have this kind of perfect area of convective initiation. But of course, there are limitations with polar orbiting satellites. For one, they only provide snapshots of the storms, so we aren't able to see the full life cycle of the storms and evaluate how they evolve across time. Of course, satellites are really far away, so maybe we aren't able to resolve the fine-scale details associated with these storms that we would be able to from ground-based or airborne instruments. And convective parameters associated with severe storms aren't captured from satellites. So we really don't have a good understanding of the surface conditions and the environments that these storms form in based on the lack of ground-based observations. So this kind of motivated the RELAMPAGO and CACTI field campaigns, which occurred in 2018 and 2019 in subtropical South America, which you can see a map of here. RELAMPAGO occurred from November 2018 to December 2018, I'll say, but the radar data I'm going to look at also extends into January of 2019. And CACTI was its sister campaign, which was funded by the Department of Energy here. And this was a little bit longer, occurred from October 2018 to April 2019. So based on this RELAMPAGO dataset and cacti, we have a lot of awesome ground-based observations now. So I have a couple of questions that I'll be talking about today, which is focused on my PhD work. The first is very broad scale, synoptic scale. How do the Andes and the Sierras de Córdoba influence the environment and resulting MCSs under different synoptic regimes? Second, I'll go down a scale and look at mesoscale details of these MCSs and determine how well models capture these mesoscale characteristics, and determine how the Sierras de Córdoba influence these convective characteristics. And then finally, I'll take it down a step again, and we'll be looking at the electrical and microphysical characteristics of these storms and determining how well the model represents these as well. So most of this research uses either radar observations or model simulations. So the two radars I've been looking at are the CSU C-band radar, which is called CHIVO. And this radar was deployed for the entirety of the RELAMPAGO campaign. It is dual polarization, which means it's able to see more information about the hydrometeors. And it conducted PPI scans, which are 360-degree scans that go up in elevation each time. It also conducted a couple of sector scans, which are basically PPIs, but only over a select angle, in this case, 135 degrees. And it also completed RHI scans, which are cross-sections at different azimuths. And the PPI cycles occurred roughly every 5 to 10 minutes, depending on what scanning strategy it was in. Also looking a little bit at the CSAPR data, which is from ARM. This radar was operating during the entirety of cacti, and it is also dual polarization and completed PPIs, RHIs, as well as these HS RHIs, which are called hemispheric RHIs, and they're basically RHIs that go up and then they continue to go down the other side. So you get this broad curtain of the storm. And these PPIs cycled through every 15 minutes approximately. So one thing that I've been focusing on is identifying intense convection and different features within the radar data. And I've developed this precipitation feature identification code or algorithm, which basically looks at radar data and identifies these precipitation features in total. And then it also breaks it down into these storm modes, which are deep convective cores, which are basically just really tall storms that reach over 10 kilometers. Wide convective cores, which have areas greater than 1,000 square kilometers. Deep and wide convective cores, which are a combination of the two. And then broad stratiform regions, which are stratiform areas that have at least 10,000 square kilometers. So I'm able to basically look at reflectivity at different levels to determine these different storm modes, and then as well as the convective stratiform partition. So now I'll move on to my model simulations. I am using WRF for this analysis. I have 27, 9, and 3 kilometer WRF nested domains, which you can see here across South America. And I'm focusing on these two cases. The first one is the 13-14 December case, which I'll be referring to as the strongly forced case. And also the 25-26 January case, which I'll be referring to as the weakly forced case. And these simulations were run with the CONUS physics suite, as well as the Thomson aerosol aware microphysics scheme. They are forced by ERA 5 reanalysis data, which is hourly and quarter degree resolution. And I've also applied some terrain modifications to these runs to see how the Andes and the SDC impact the environments, which I'll show in the next slide. And then to look at more of the mesoscale details, I've run an additional 1 kilometer nest, which is focused right along the SDC here. And that's only completed on a couple of the different runs, but I'll show some results from those later. So in terms of terrain modifications, I have basically 5 different runs I'm looking at. The first is a control run where I don't change the terrain at all. The second is the no SDC run where I basically remove this feature here. The third is a low Andes run where I reduce the height of the Andes by 50%. The fourth is low Andes no SDC, which reduces the height of the Andes as well as removes the SDC. And the final one is a no terrain run, which I basically set everything in the domain to be 0 meters. And this works by, I basically select boxes around the area of interest that I want to modify. And I go in and set that value to the value that's downstream of that. So for a lot of the SDC cases, it's between like 60 and 100 meters. And then I'll apply some smoothing around the edges and then basically repeat this process until I get something that looks reasonable and that's not, doesn't have any sharp gradients or anything that would alter the storms that do develop in the model. So these are the 2 cases I have been looking at. These are the strongly forced MCS is on the left here. This is a snapshot from GOES 16 of the brightness temperatures, channel 14, infrared brightness temperatures from 3 UTC. So this is when the system is really ramping up here. And this MCS was associated with a really deep upper level trough, strong least cyclogenesis, and a strong low level jet, which are all the ingredients that were hypothesized to be necessary or important for formation of these MCSs in this region. In contrast to that, I have this weakly force case, which is from January. You can see it still produces a huge MCS, but the flow aloft is mostly zonal. There's really not much least cyclogenesis, and there is a jet, but it's a lot weaker than in the strongly forced case. So I think these provide a really good comparison to see how the terrain impacts these and what the role of the environment is. So before I get into more of the results, I just wanted to put this kind of in context of the rest of the RELAMPAGO field campaign. How do these cases compare to others? So this is Hav-Mahler diagram, which I'll be showing a lot of, so I'll walk you guys through it now. We have time increasing on the y-axis here. So it starts from November and ends in January. And then longitude is on the x-axis here, and I'm averaging over a certain latitude band. In this panel here, I am showing the 500 millibar anomalous heights, where the reds are anomalously high and blues are anomalously low. And this contour here is the terrain profile. So basically the Andes are here. So if we look at the weakly force case, which occurred in January again, we see that it occurred under anomalously high conditions compared to other times during the field project. And this plot over here is showing the 850 millibar meridional winds, or the north-south winds, with the blues are northerly and reds are southerly. And we see that occurs under a pretty weak low-level jet regime. If we look at the strongly forced case now, which is the December 14th case, also IOP 17, we see that there's a really anomalously deep upper level trough that comes through, and that is associated with a pretty strong low-level jet, as well as a wind shift between the north and the southerly as a lee cyclone moves through. Additionally, I wanted to show how the actual MCS compares to other MCSs or other precipitation features observed during RELAMPAGO. So this is a plot from all the precipitation features identified in the CHIVO radar dataset from November to January. And this is showing the areas. So if we highlight the 2 cases of interest, we can see that both of these cases reach a maximum of over 50,000 square kilometers. And you can see we also have some really big events in the beginning of January here. However, when we look at the volumetric rain, which is now taking into account the rain rates, and we highlight these cases, we see that these actually have the highest rain volumes out of all of the other times observed by the CHIVO radar. So these cases dumped a lot of rain in the region, which is very important for severe weather and flooding. So I'll start with my first question, which again is kind of large-scale synoptic thinking. First is, how do the Andes and SDC modulate the environment and MCS under strong and weak synoptic forcing? This work has been published in this paper back in September in Monthly Weather Review through the AMS, if you want to take a look at that. So I'll start with looking at the 500 millibar heights. These, again, are Hofmahler diagrams, but in this side is the strongly forced case, and then I'll show the weakly forced case on the right here. The top plot is the control run. The middle plot is the low Andes minus the control run, and the bottom is the no Andes minus control run. So what we see in the control run is that for the strongly forced case, we have a pretty deep upper level trough that approaches the west coast of subtropical South America, but it doesn't really extend past the Andes that much. It kind of gets sheared apart. However, when we reduce the Andes and when we remove them completely, we see that the trough is actually able to completely make its journey across the Andes intact. It's not being sheared apart. So you actually have deeper heights on this side of the Andes. If we compare this now to the weakly forced case, these are on the same color bar, so you can see that this case had a much weaker upper level trough that comes through. It's actually kind of like a short wave across the mid latitudes, and the flow across the SDC is actually pretty zonal. But when we look at the difference plots for this case, you can see that we don't really see that same signature. And honestly, it's pretty similar between, and even actually starts to, the trough aloft actually decreases a little bit. If we go down to 850 millibars now, this is basically looking at the Lee cyclone. I've zoomed into the Cordoba region here, so now we have the SDC here, and we don't really see the whole height of the Andes. But what you can see here is that in the strongly forced case, we have a strong Lee cyclone that develops in the evening hours, basically over the higher terrain and the SDC here. And when we reduce the Andes by 50%, that Lee cyclone weakens, which makes sense because we don't have as high of a barrier anymore. And when we remove the Andes, we no longer have a Lee cyclone because there are no mountains. And when we look at the weakly forced case, for this control run, we see that there is still a Lee cyclone over the terrain. It's significantly weaker than in the strongly forced case, though. And similar effects occur when we reduce the Andes and remove them completely, where we have a weaker Lee cyclone or we don't have one at all. So now I will look at how the terrain influences the South American level jet in the form of winds and moisture on the next slide. But here we have Hofmahlers again over this region. This time we just have the control, the low Andes, and the no SDC, or no Andes at all. And in this case, green is from the north, so that's highlighting that South American level jet. And what we see for the strongly forced case is that we have these two bursts of northerly winds that occur pretty far east over the plains. However, when we reduce and remove these Andes, we don't really get that secondary burst anymore, which is interesting. And then, of course, we still have northerly flow, but it's not considered a low-level jet when we remove the terrain because the low-level jet is partly there because of the sloping terrain of the Andes. When we compare this with the weakly forced case, we see that there is a pretty strong signature of northerly flow directly downstream of the SDC, so it's really shifted in towards the terrain. And when we reduce and remove the Andes, we still see something fairly similar. It doesn't really change in magnitude as much compared to the strongly forced case. Next, I'll look at moisture anomalies associated with the low-level jet. So for the strongly forced case, we see that most of the domain is in this blue-green color, which shows that this case was anomalously moist compared to the last 40 years or so. And this maximum occurs right over the SDC here. And when we reduce the Andes by 50%, we actually have this drier air coming in a lot sooner compared to in the control run. And this happens even quicker when the Andes are removed here, and that kind of suppresses all the convection to the east. And this influx of dry air aligns pretty well with the wind shift from northerly to southerly as the lee cyclone moves through. For the weakly force case, we can see that this is also anomalously moist across most of the domain, but the maximum does occur over the terrain further in. So there's this shift of moisture further westward, which has been documented in some of the previous literature. And this actually looks pretty similar, again, when we reduce the Andes by 50%. And when we remove them, we do see some drier air coming in when we don't have that terrain anymore. So you may be wondering, okay, what do these MCSs actually look like in these simulations? So these are just snapshots from 3 different times of the system in the control, the 50% Andes and the no Andes runs. And this is for the strongly forced case. And what we see is that there's a linear system that develops in basically all the cases. I mean, there is one when there's no terrain, it just occurs a lot faster. And when we reduce the Andes or remove them, you see the intensity of the MCS generally diminishes, and it also propagates a lot faster to the east, and you don't have that connection as much to the terrain. If we now look at the weakly force case, we actually see something kind of similar, where most of the convection in the 50% Andes and the no Andes moves a lot faster off, and there's not as big of a connection. And one of the panels I really like to highlight is this one here, where we have still enhanced precipitation between the SDC and the Indian foothills, which you don't really have as much of in the 50% Andes runs. And of course, you don't have that at all when there are no foothills. So to summarize this part, I thought it would be best to do it in like a cartoon version, so hopefully you'll be able to follow along. So for the strongly forced case in the full Andes control run, we had a fairly deep upper level trough, which produced a pretty strong lee cyclone. We had strong northerly flow, which brought in significant moisture into the region along the low level jet. And this resulted in a pretty significant linear MCS. When we reduced the Andes by 50%, we actually saw that the trough was able to make it over without being sheared apart. But the lee cyclone ends up being slightly weaker, and the low level jet and the moisture associated with it is also a little bit weaker. And this results in faster propagation of the MCS to the east, and also not as strong of an MCS in general. And then finally, when we removed the terrain, we found similar, the trough was able to basically just come right over because there was no influence with it. There is no lee cyclone because there are no mountains now, so we don't have that anymore. We still have northerly flow, but it's not considered a jet anymore since we don't have that terrain. And we also have drier air coming in. And the system basically just rapidly moves off to the east and diminishes. Compared to the weakly force case now, we found that flow aloft was mostly zonal, which produced a modest lee cyclone. We still had a low jet. It wasn't as strong as the strongly forced case, but we still had a pretty significant MCS that developed. When we reduced the Andes, we saw that there really wasn't much of a difference in the upper level flow. The lee cyclone was slightly weaker, but still there. And the jet really didn't change that much when the Andes were reduced. And this still also produced a pretty strong system, although the location and timing, of course, was different compared to the control run. And then when we removed the Andes, again, we basically saw a very similar upper-level flow. We don't have that lee cyclone anymore. We still have northerly flow, but it's not a jet. And we still had moisture. It was a little bit, we did have some dry air coming in though too. So the air was a little bit smaller there. And of course, we still have this MCS that moves off. So in words, basically, the Andes alter the environment more under strong synoptic forcing. And the MCS seems to have more interactions with the terrain under weak synoptic forcing, at least in these model simulations. So now I'll move on to the second question I'm interested in, which is looking now at the mesoscale. And this, again, is how well does the model capture the mesoscale details of the MCS, and how do these SDC alter the convective characteristics? This work has been written up. It's going through some revisions now before we submit it, though, so hopefully that will be coming through shortly. So for this mesoscale stuff, I've started to incorporate the radar data, which you'll see. I've been mostly using the Chivo data since that is from CSU. So for here, we are now looking at the reflectivity from this strongly forced case in still a Hofmahler plot, so time on the y-axis, longitude on the x-axis, and now we're just focusing over the radar domain. And here's the terrain profile, so you can see the Sierras de Córdoba here. And what we find in the observations is that there's a fairly strong convection located over the terrain. And there's a couple of different backbuilding components to this, which kind of locks in this convection to the terrain. When we look at what happens in the 1 kilometer control run, we see that there are similar convective episodes that occur over the terrain here. Of course, the timing and location is a little bit different compared to the observations though. And when we look at the 1 kilometer no SDC runs, we see that there's a pretty strong convective feature, but there's no SDC here anymore, so you don't really see that backbuilding component as much. Comparing that now to the weakly forced case, this MCS had kind of two components to it, I guess. The first is this really intense deep convection that occurs in the afternoon. And this was actually the strongest or deepest convection we saw observed from the Chivo radar with 40 dBz echotops above 20 kilometers, which is super deep. So these systems pass through in the afternoon off the Sierras de Córdoba. And then we have the secondary, generally more stratiform event that kind of just sits over the terrain for a very long period of time overnight. When we look at the 1 kilometer control runs for this, we see that the model doesn't capture the timing of the deep convection that well. It's actually fairly delayed into the overnight hours here, but we still have that pretty strong connection to the terrain here, which is nice to see. And then when we remove the Sierras de Córdoba, we see that a strong system still develops, but we don't have that stratiform connection to the terrain here like we have in the observations and in the control run. So now I'm bringing in the precipitation features that I mentioned earlier. These are plots of just the deep convective cores, so basically the really tall ones. And again, we have the strongly forced case on the top here for the observations, the 1 kilometer control, and the 1 kilometer no SDC runs. And what we find is that these deep convective cores are generally scattered across the domain. There's not necessarily a strong connection to the terrain. But this black line highlights the track of the MCS, and you can generally see that this is fairly similar across all these simulations as well as the observations. If we go down to the weakly force case, we see a different story. So in this observations and in the control run, a lot of the deep convection is focused along the SDCs here, and we don't see a lot of it over the plains like we did in the strongly forced case. But when we remove the terrain, you do see that it's pretty widespread and there's no connection anymore to the terrain. And the MCS tracks are actually fairly similar between the observations and control run again, where it basically just hangs out on SDC for an extended period of time. But when we don't have the SDC, you can see it basically just slowly propagates off to the east. So we were interested in determining basically the ecrotop heights and how many of these deep cores were observed in terms of pixels. So for the strongly forced case, what we find is that the model, both the control and the no SDC, significantly overestimate the number of deep cores. This black line is the observations from Chivo, and then these other two are from the model. So throughout the life cycle of the MCS, the model is overestimating 2 to 3 times the number of deep convective cores that were observed in the radar data. And something is similar for the weakly force case. Of course, the timing is different. A lot of the deep convective cores occurred in the beginning or in the early evening hours in the observations. But even if this was aligned better, you could see that once again, the model significantly overestimates the number of deep convective cores. And kind of tying into that, the models underestimate the amount of stratiform precipitation, which is fairly well known. But we see this in the form of the different broad stratiform regions. So these again are like the really large stratiform areas. And what we see is that these generally occur along the SDC in the observations. And they're similar locations in the model run, but there's just a lot fewer of them, and they tend to be smaller compared to the observations. If we look at the weakly force case, this was associated with a lot more stratiform, so there's a lot more dots here. And generally, you can see that the observations and the control run are in agreement fairly well, where we have stratiform basically following the MCS track right along the SDC here. And when we remove the SDC, we don't have that connection to the terrain. So again, it just moves off to the east. So that's kind of the MCS overview and convective characteristics. So we wanted to dive in a little bit more into what was driving these differences. So we looked at cold pools in the model data. We do not have cold pool observations, at least from the January case. I think there's a couple from the December case, which we haven't looked at yet, but these are just comparing the models together now. So the blue shading here is the virtual potential temperature perturbations. So the darker blues are basically higher perturbations or the cold pool locations. At 2 different times, this is from the strongly forced case for the control and the no SDC runs. And these colored contours are the reflectivity, and this is all occurring at the lowest model level. And what we found is that cold air has similar strengths between the control and the no SDC runs, and it occurs in similar locations. And looking at this more, we think this is primarily just due to the passing cold front and not necessarily associated with the MCS itself. And when you average these values across the entire domain, you actually get almost the same between the control and the no SDC. There's like 0.2 Kelvin difference between the two. So they're very similar. Contrasting that with the weakly force case though, we show that cold pools generally form or get trapped, I guess, between the Sierras de Córdoba and the foothills here. And that's kind of what helps to drive initial or reinvigorate precipitation in this region. And when we don't have the Sierras de Córdoba here, we have more dispersed cold air. And as a result, the system just kind of moves off to the east. So to look at that a little bit more, we did a couple of cross sections to see how deep this cold air extends through the atmosphere. And these cross sections are taken across the Chivo radar at, for this case, just 6 UTC. So this is basically right after the storm is moving through. And what we see is that cold air is generally concentrated within the lowest 2 kilometers. And the results are fairly similar between the control and the no-STC. That actually might be even a little bit colder in the no-STC, but it's generally pretty widespread. Compared to the weakly force case, though, we see that a lot of the cold air is pooling between the STCs and the foothills, which we showed in the maps on the earlier slide. This air is colder air is a little bit deeper, like 2.5 kilometers. And when we remove the Sierras de Córdoba, we see that it's a lot more dispersed across the plains following the MCS. So to summarize this part, I also went with cartoon characters. So for the strongly forced case in the observations, we saw that the deep convection was pretty widespread across the domain. And we had some also broad stratiform regions that were identified. In the control run, we had widespread deep convection again, but it was generally deeper and there was a lot more of it compared to the observations. And as a result of this, the stratiform areas were a lot lower compared to the observations. And the cold pools that developed were pretty widespread and were generally forced by the synoptic flow. And then when we removed the Sierras de Córdoba, we saw something pretty similar, widespread deep convection across the domain, which was significantly more than in the observations. Also weak broad stratiform regions and also pretty widespread cold pools. Comparing that with the weakly force case, a lot of the deep convection was concentrated along the Sierras de Córdoba. We had broad stratiform regions that were very expansive, and there was a lot of them that basically occurred right along the Sierras de Córdoba for an extended period of time. In the control run, we saw something similar. The deep convection was concentrated along the Sierras de Córdoba. We did have stratiform regions. They were still a little bit smaller than in the observations. And the cold pools that developed were pretty deep, but they were confined to the west side of the STCs, which kind of helped to reform precipitation in that region. And then finally, for the no STC case, weakly forced, we saw widespread deep convection, similar to the strongly forced case. We had broad stratiform regions that existed, but they were smaller compared to the observations and control run. And the cold pools that developed were not as strong and were pretty widespread. So for this section in words, the strongly forced MCS has widespread convection, which is significantly overestimated in the model. Cold pools in the strongly forced case are likely driven by the synoptic flow in the model, not necessarily the MCS. And enhanced precipitation occurs along and west of the STC in the weakly forced MCS, and this is primarily driven by the cold air pooling in this region. So finally, I have a couple quick slides on current work, which I'll be working with Rachel on down at USP. And this is focusing more on the electrical microphysical scale. So I'm interested in looking at and analyzing the electrical characteristics of these storms using the LMA data and the GLM sensors, as well as evaluating the lightning parameterizations, which are applied to these model simulations that I just showed. And then kind of a side project I've been working on is estimating vertical motions from the CSAPR radar. So something that I'm interested in is where the lightning maximizes within the storm and how does that relate to the location of the STC. So these dots represent the different flashes from this time from the LMA. And so I basically want to see where do these flashes occur, as well as separate them into convective and stratiform flashes to determine these characteristics. I plan on using the LMA and GLM to look at flash characteristics associated with these storms. There's a list of them here, but for example, different flash areas associated with convective and stratiform flashes, flash heights, total flash energies, and flash durations are a few of the parameters I'm interested in looking at. The next thing looks at the model simulations and tries to determine if lightning parameterizations, which are mostly based on United States storms, can be used in this region to accurately represent the electrical characteristics of these storms. So we have a couple different lightning parameterizations that we plan to look at. I've highlighted the 35 dBc echo volume here for the observations and the 1 kilometer wharf runs, as well as the grapple and hail mass across the domain, which is integrated through the column, and the grapple mass associated with the control model simulations. So we plan on comparing these, seeing how well they agree with one another, and trying to basically back out lightning parameterizations for this region. And then finally, like I said, this is kind of a side project, but it's pretty interesting, is basically looking at the distribution of vertical motions, which are derived from the radar. So if you remember when I mentioned earlier, the CSAPR radar does these HSRHIs, which go up and then down the other side. So there's a brief moment where the radar is pointing straight up, and we can basically get the vertical motion from that. So I'm still working on a methodology for this. I haven't corrected for the fall speeds yet, but we're working on that. But basically, we want to get these observations of vertical motions, which are notoriously hard to achieve, and compare that to what the models show, because models are known to significantly overestimate vertical motion. I have similar plots for this for the model simulations I run, and these extend out to like 80 meters per second, which is pretty insane because these only go to 10. So there's definitely something we need to work on in the models, I think. So with that, I'll go through my conclusions. The Andes play an important role in modulating the environment, especially under strong synoptic flow. But strong MCSs still occur under weak synoptic flow, which we saw with the weakly force case. And these appear to be largely driven by the interactions with the terrains, especially the Sierras de Córdoba. And unfortunately, the mesoscale details are not really well captured by the models, more specifically these models that I have run with. And this is especially true under strong synoptic flow. So some implications for this work. Obviously, this will hopefully lead to improved forecasting of severe weather in the region if we better understand how and why these systems form the way they do in the region. But related to that, and I think pretty importantly, these model simulations have shown that we really need some sort of data assimilation of ground-based or satellite-based or whatever, some sort of observations into the models that will hopefully improve the complex terrain flow features that are known to occur in these regions, and especially under stronger synoptic forcing. So with that, thank you, obrigada. Here's my email and website, and I will be visiting. I'm leaving tomorrow. I'll be there Monday, and I'll be down there for a month. So if you want to come talk to me about anything, I'd be happy to chat. So yeah, thank you.
I don't know if you can hear the claps, but they were clapping here.
Yes, thank you.
Thank you very much, Marqi. So do you have any questions? Don't be shy, people.
I have one. How do you did the simulation? You use 3 domains, okay? But the domain are nested one way or 2 way?
I believe it's one way. And then we ran N down to get an additional 1 kilometer. So I think that would be 2 way.
One way? Yes.
I think so, yeah.
I think so.
Any other questions? No? They are shy. They will ask you when you come, you see.
Okay.
But I have one.
Sure.
I'll ask mine, and then Jose can ask hers.
Okay.
Do you know why your model, like, I mean, all the simulations you did overestimate the number of the deep convective cores?
That is not something I have really looked into, but it's fairly well known that models tend to overestimate convection as well as updraft speeds. So I think that kind of ties into the updraft analysis, which I'm looking into. I assume it has something to do with the vertical motions, but I haven't changed any of like the physics or anything. This is just one set of runs. So it could be a lot of different reasons, I think.
Mm-hmm. No, but, and I'm curious, in those 2 cases you are studying, did occur any severe weather, like, I don't know, hail, or, I don't know, strong winds?
Yes, I believe both cases had hail. I'm pretty sure that's because there's a lot of observations, because that was still technically in the RELAMPAGO timeframe. I believe the January case also was associated with some hail, and of course flooding was big.
Yeah, not amazed usually. There is a question here. It's from YouTube, I guess. So excuse, can you read the question? It's very blurred here. Oh, now I can see. So he is excusing himself because he arrived late. And then I would like to know if there were studies on the wind direction and intensity in the attempt to understand the orographic influence.
We did not specifically look at the mesoscale flow features. It was mainly just the synoptic analysis of the low-level jet. There's been some work done by IT Singh, who's a postdoc here now, looking at idealized models and the flow features around the Sierras de Córdoba. But that's not something specifically that I have looked at in the models, no.
Okay, Jose.
Please, in the end of the figures, did you show some vertical velocity peak figures? The negative is upward or downward movement?
Most of it is downward motion we're seeing, which has been kind of interesting to us. We thought there'd be a lot more upward motion, but it seems to be heavily skewed towards the negative side. So
the upward, okay.
Okay. More questions or no? No? Huh?
Next week.
Ah, yeah, they're saying they have questions next week for you.
Okay.
So thank you very much, Marqi, and we are very anxious to see you Monday.
I'm excited to come. I can't wait to meet you all.
Okay, bye-bye, and thank you very much.
Thank you.